Hi, and welcome to this series of lectures on measure theory. So, what is this? Well, I'll first define what this is not. This is not a verbal regurgitation of Rudin. This is not a revolutionary new way to study measure theory. Well, then, what is this? So, my professors once told me that the best way to do mathematics is to talk mathematics, because talking mathematics, well, it reinforces your thoughts and gives you a grasp over really your own mathematical thinking. And I really feel like doing maths, so I suppose this is my way of doing it. So, let's get into it really. So, what are the prerequisites for this course? So, for this series of lectures on measure theory, you should have had some experience with the subjects of real analysis, topology, some basic set theory, and vector spaces. So, when I say you should have had experience with these subjects, what I really mean is you should have at some stage formally studied these subjects. So, if maybe you don't recall the proof to Bolzano-Weierstrass theorem off the top of your head, or you don't really remember what is the structure for the proof of Rolle's theorem, that's completely fine. But as long as you have studied, as long as you can recall what a sequence is, what the limit of a sequence is, what a continuous function is, what as long as you can recall like the real fundamentals of these subjects, you should be more than fine. Almost everything that we will study in this subject will be self-contained within this lecture, this series of lectures. But you should know the basic fundamentals of real analysis. Again, it's the same for topology. You should know what a metric is, what's an open set, what's a complete metric space. Just as long as you have these definitions in your head, that's completely fine. You don't really need to recall theorems, or you don't really need to have all of these courses fresh in your head. For set theory, again, really rudimentary set theory, you should know what unions are, you should know what complements are, you should know what a countable set is, you should know what an uncountable set is. You should be able to recall the fact that a countable union of countable sets is a countable set. And for vector spaces too, you should know what a field is. You should know like what the basic definition of a vector space is. You should know what the basis of a vector space is. You should know what the dimension of a vector space is. As long as you have the fundamentals that's really covered during the initial stages of each of these courses, as long as you have that in your head, you should be more than fine. So then, right, this lecture over here is really just to provide some motivation. If you'd like to get straight into the maths, I'd suggest you move forward to lecture 1. But this entire series of lectures is really designed upon feeling really the subject that you're studying, pondering upon the definitions, really seeing if you can get the true meaning behind the theorems. So if you really are all about just the raw, definitions, lemmas, theorems, and proofs, this isn't the best place for you to begin with. But if you'd like to get into the maths, lecture 1 it is. But coming to the motivation for the subject. So what is measure theory? As the name implies, what we'll be doing is we'll be developing the theory to really define the meaning of measuring something. What are the things you can measure anyway? You can measure the height of a building, the area of a pool, the volume of your aforementioned pool. You can measure the probability of you getting a heads when you flip a fair coin. You can. The notion of measuring things exists in many places, but we'll be developing the theory for the one I suppose that's the most fundamental. We'll be developing the theory to measure subsets of the real line, the usual real line that all of y'all have studied, during real analysis. So, if you have studied Riemann integration, you would know that we had some notion of measurement there too. We had defined really the meaning of the area under a curve, a continuous curve. other types of curves as well, but we did define the notion of measurement for a continuous function. So there, if you may recall, we had essentially a slight, I would say, assumption. The assumption we made at the stage of real analysis was that if we had a continuous function and you wanted to calculate the area under this curve, you'd draw these rectangles really. And you'd calculate the area of these rectangles by summing up, the height times the width of each of these rectangles. So you did define really the area for a certain category of sets. You did define the area of a rectangle to be the height times width. It wasn't axiomatically stated anywhere, but there was this, to derive the meaning of an area under a continuous curve, you first defined what is the area of under step functions like these. That was the height times width for each of these rectangles. So similar to that in measure theory, for the real line, we will define the starting notion of measure with a very, very familiar set on the real lines, which are open intervals. So this is what I call the law of the land. What does the law of the land say? It says that for any open interval a comma b, which is a subset of the real line, the length of a comma b equals b minus a. This is a definition for the measure, the length of a subset of the real line. Very natural. I don't see many of you opposing this definition. It feels very natural. So, yep. So then let's, get some examples down and let's see how far this notion really can take us. So if I have a set A, if I have a set A, which is open 0, 1, the length of this, by my definition, which I just stated, would happen to be 1 minus 0, which is 1. So really no problems here. If I look at the set B, which is 0, 1 union 2, 3, if I asked you to tell me the length of this set B, and if you answered 2, what would I do? I'd immediately put you in jail because you just violated the very law I gave you. The law said that for an open interval, the length is b minus a, but the set B is not an open interval. It is the union of two disjoint open intervals, but it is not itself an open interval. So right now you can't really, the length of the set B is not really defined. But if we were to tread down this path of developing a theory to measure the length of subsets on the real line, I suppose you would also agree that a very natural property you'd expect would be that if I have two disjoint sets A, B, then the length of A union B would be the length of A plus the length of B, since they're disjoint sets. So it is, quite natural. It is very much in our favor to develop this theory in such a way that this property would be true. So right now, if I assume that this property is true, then yeah, the length of B is 2. But, we would have to assume this property in our head. So you can maybe start to see some of the structure that we would follow while developing this theory. So, let's move on to the set C, which is closed 3, 5. Again, if your answer immediately is 2, I would say that great intuition, but still, you can't at this stage tell me its length is 2 because the only law I have is the one that states that for open intervals A, B, the length is B minus A. Closed 3, 5 is not an open interval. So we would have to find out some way of calculating the length for this. I would agree with you that we should arrive to a conclusion at the end where the length of C is 2. but we must develop a way to achieve that. So to do this, what we'll do is, what calculus does best is taking limits. Really, anything in life which you want to calculate something for an object that you're not familiar with, what you do is you take objects that you are familiar with, construct a sequence of them which leads you to your object that you don't know, take limits, and boom, you have it. So that's what I'll do here too. So let's define an to be the set 3 minus 1 by n, comma 5 plus 2 by n. 5 plus 1 by n. What is an? An is an open interval. So by the law of the land, I know that the length of an will be, what is it? 2 plus 2 by n. No assumption here, nothing that I've taken for granted. This is derived from the very law I stated above. So I do have that the length of an is 2 plus 2 by n. Now, if I were to ask you, where does the sequence of sets an, like to which set does this sequence of sets an converge, then I think it's quite visible that an, that the limit n tends to infinity an will be equal to c. Yeah, I'm not being too pedantic about, convergence in what sense. It's pretty clear. We don't need to get into that at this stage. But I suppose all of y'all could see that 3 minus 1 by n to 5 plus 1 by n, which, would be something like here to here, then here to here, here to here, and so on. This sequence of sets does converge to closed 3, 5. That's not 5, that's 4. Whatever, you get the point. So limit n tends to infinity an is our closed set C. So if I wanted to define the length for C, what I would simply do is the length of C would be nothing but the limit n tends to infinity length of an. Quite smart. So where does this 2 plus 2 by n converges to 2? So I will define the length of C also to be 2. So we have now essentially expanded our sets for which we can calculate their length. So it's now open intervals, disjoint union of open intervals. We now have closed intervals. What else can we do? So far it really hasn't defied our intuition too much. We seem to be going along a path that's, not too polarizing. But when we can choose, so you know what, I'll just give you the set. Now I'll try to give you a set which is not as nice as these open intervals. It is and the set of natural numbers. It isn't immediately obvious what this length of such a set could be. I think when I was asked this question initially, my answer was it was infinity. Yep, that's what I thought. That's what I would define the length of this to be initially, because I thought, well, it has, an infinite number of points that really are spread out on the entire real line. So, they're here. They're there everywhere. So I couldn't really argue that why I couldn't really see why it should be anything other than infinity. But if you do think about it a little bit more, what is if you do think about it, may not necessarily be infinity, because if I define my set an, sorry, if I define my set an to be equal to well, let's define an to be this set. So right, can we let's try to see how this goes. What's a1? A1 equals just 1, which can be written as closed 1 comma 1. So the length of a1 can be defined, is now known to be 1 minus 1, which is 0. a2 is 1 comma 2, which is 1 comma 1 union 2 comma 2. Again, remember, we do expect that the length of the union of disjoint sets is the length of each of those sets combined together. So this would also be 1 minus 1, which is 0, plus 1 minus 1, which is 0, 2 minus 2, which is 0. This would also give us 0. You could see this way that the length of each an would be 0. Since we do, well, in some sense, these set of ans converge to the set of natural numbers. No need to get too much into detail about convergence in which sense. I'm just trying to get things across intuitively. You can also see that if we want to define the length of these weird kind of sets using limits, then the length of an, then the length of, our set D, the length of natural numbers would be equal to the length of the limit of this, of the length of an. Wow, I shouldn't have written here. Which is the constant sequence 0. So its limit is 0. So we have now concluded that the length of natural numbers is in fact 0. Which is not as per what my initial intuition had told me, but I somewhat can take this. So if you notice, there's something nice about this argument, that if we have any countable set, this argument will work. So there was nothing really special about this collection representing subsets of natural numbers. This proof would really have worked if you substituted natural numbers for rationals. I don't know how to write that. I don't know how to write Q in the rational numbers way. Anyway, the same argument works for Q as well, right? Rationals are certainly countable. So just list all the countable sets, go on taking one at a time. Length of each of those sets is 0. So the limit is, the limit is also 0. So we can conclude that the length of irrationals is 0 as well. So maybe the length for every countable set is also 0, but things will get weird when we get to uncountable sets. So yep, you can somewhat see, I think this is enough to see how we will progress with the development of this theory and just what we can expect really. So just some more food for thought. We could maybe just think about some questions which we could ask while we study this subject. So, the first question is, if A and B are two disjoint sets, then is the length of A union B equal to length of A plus length of B? As discussed before, this is very natural. We should proceed in such a way that we do obtain this result. So I say yes, that should be the case. Another question you could ask is, should two sets with the same cardinality have the same length, whatever that term really means. We kind of have defined it somewhat, but we don't really know the formal definition for it yet. So your knee-jerk answer might be yes, that if two sets have the same cardinality, they should have the same length. But that's not really the case. The open interval 0, 1 and open interval 0, 2 have the same number of uncountable points, but clearly their length is not the same. So this notion of measuring the length of subsets on the real line is distinct from cardinality. They may seem somewhat related, but the notion that we will study is not really that correlated with cardinality. So the answer for this is no. Not always. The next question is, should the length of a set change if you move it around? Layman terms for is the notion of length translation invariant. And I would estimate that yes, it should be translation invariant, because you see the real line is it's a straight line. The behavior of the line does not really change if you're in 0, 1 as opposed to 10 billion, 10 billion plus 1. So just translating the set in any direction shouldn't really affect the length. So we would say yes, that we do want, no, we don't want this length of the set to change. And I suppose the last question is, should every set even have some length? This one's a bit more, this one's a bit tricky to think about, because the way we defined area under the curve during Riemann integration, it was kind of giving you a notion of measurement on continuous functions. It would give you the measure of how much area lies beneath them. And when we were studying that, if you've studied that, you would have absolutely come across the Dirichlet function, which is really 1 on rationals and 0 on irrationals. So it's defined on the whole real line. You could even work on closed 0, 1. But we failed to define the meaning of some area under the curve for this function. So maybe so we did fail to define some notion of area. Will the same thing happen here? I mean, God knows. I suppose we'll find out. But yeah, I think this should kind of give you some sense of the direction which we'd be proceeding. And I think the last thing I'd like to state is why I chose to start with the subject measure theory with this journey on YouTube. So while some people would say that measure theory is really real analysis part 2, it's an extension of real analysis from where Riemann integration ended. I would kind of disagree with that. It is an extension, because you would be, I guess, starting off from where Riemann integration ended. But the way measure theory works is quite different. You see, in real analysis, the real numbers were always shown in what I feel is kind of a very knight in a shining armor kind of way. Nothing about the real numbers was unexpected during my study of real analysis. Functions which go from negative to positive continuously do take on the value 0. I mean, did that shock you? Rolle's theorem, that the derivative, that if a continuous function, is going in this way, and it's also differentiable, then the derivative should have been 0 at some stage. Did this really surprise you? No, not really. So the joy from real analysis that most people experience comes from the way we studied the subject, the rigor that I think was introduced to students. That's what makes real analysis special, not the results itself. But in measure theory, I think the reason why I really like measure theory so much is that it shows you that the real numbers are not perfect, that they in fact do defy our intuition sometimes. Like we will come across results during the series of lectures that will oppose your intuition. I mean, think about the last theorem in real analysis that defied your intuition. Nothing comes to my head immediately. So this does show you that there are a few chinks in the armor of the real numbers, and they are not quite as perfect as real analysis made it out to be. So, there will be sets that will be so, they'll misbehave so wildly that they produce results that are just bizarre. I mean, an example I can think of is the Banach-Tarski theorem. I think that's what it's called. Essentially, what it says is if you have a unit cube in three-dimensional space, then there is a way in which you can cut that cube in finite number of pieces. You can cut it in 5 pieces. If you do rearrange those pieces, then you can end up in a configuration where you would have 2 identical unit cubes. So you take one unit cube, chop it up, reassemble the pieces, and you'd have 2 unit cubes. It seems bizarre at first. It makes absolutely no sense. How can you produce double from nothing, from just one? Feels like you're violating some law of physics. Something must be going wrong somewhere. But no, it's a theorem that is true. There is a valid mathematical proof for it. So it just behaves in such weird ways that you can't really wrap your brain around it. Then again, maybe this isn't surprising to you. I could take the set of natural numbers, split it up into even and odd numbers, and really, I can end up with 2 sets that are of the same size as the initial one, and yet both arose from that set of natural numbers. So maybe it isn't surprising to you, but it certainly was to me. So a lot of weird and non-intuitive results come out of measure theory, which I think is really beautiful, because there are other mathematical subjects where you can experience obviously non-intuitive proofs, but they often live in a world which is complex to begin with. So to stay stuck on the real line and yet produce results that are not immediately intuitive, I feel is quite an achievement, and that's what makes the subject special to me. So I think that's about it. That should be enough motivation, I think, to begin this course. And before we end this lecture, I'd just like to say a quick thank you to Dr. Priyabrata Bag and Dr. Pramod Kumar. So these are really what I would consider my mathematical fathers in the field of analysis. Everything from the way I argue to the way I write down mathematics to the way I talk and think about it is something that I've learned from them. So, I mean, I definitely cannot thank them enough for really the way they have trained me to do mathematics in general, not even just analysis, but to just deal with rigor and logic in general. All of that I owe it to these people. They some of the most phenomenal teachers I've ever come across. I will drop a link to their Google Scholar profiles below. I mean, most of this course is structured around most of this course is structured around really the course that Dr. Pramod Kumar taught me when I was in my bachelor's. So I'm really following his direction in this. Just phenomenal, absolutely incredible teachers. So, just a quick thanks. And, we'll study a lot. I think that's about it. And a lot of interesting lectures to come, a lot of interesting paradoxes and non-intuitive things to discuss, which I feel will be very interesting. So nice. Thank you for watching this, and see you in the next episode.